Okay, so this is 8.2. We're going to be talking about compositions of linear transformations and inverse transformations. So we'll start with some terminology. And this first term might actually be one that you're familiar with from algebra. If we have a linear transformation T that maps a vector space V into a vector space W, and if for every V1 and V2, so any pair of vectors in V, if the image of V1 is equal to the image of V2, so in other words, T of V1 and T of V2 are equal to each other, then that implies that V1 is equal to V2. We say that if this property holds for any V1 and V2 in the domain V, then T is 1 to 1. Now, if that definition seems a little difficult to wrap your mind around, another way that you can think of it is that V maps distinct vectors into W, or sorry, distinct vectors in V map distinct vectors map two distinct vectors in W. Or another way of saying that is that there's no two different vectors that come from V that have the same image. Okay, so that's what we mean by 1 to 1. Every vector in W is or every image in the range of T, I should say, is the image of only one vector in V. Another important term, well, actually, sorry, before we jump to that, I don't think your book actually uses this term, but in other courses you'll see this term used. If a function, not just a linear transformation, but literally any function from one set to another has this one-to-one property, then we call that function an injection. I may use that term here and there. I'm just throwing it in here for reference. I don't really think your book uses it, but there it is. If for every W in W, so in other words, the codomain, or the vector space that we're mapping vectors into, if every vector in that vector space is the image of a vector under V, or is the image of a vector in V, then we say that T is onto. So in other words, in the last section, 8.1, I sort of stressed this point that a linear transformation, if I use this notation here saying V is being mapped into W, this doesn't necessarily imply that every single vector in W is used as the image of a vector in V. Or in other words, W is not necessarily the range of T. The range of T is just a subspace of W. But if it turns out that W is the range of T, meaning every vector in W shows up as the image of some vector in V like this, then we say that T is onto, or that T maps V onto W. Every vector in W is used in this idea. Equivalently, we can say that T is onto if W is the range of T, like I said a second ago. Similar to the one-to-one term, when we have a one-to-one function, we call those types of functions injections. If you have a function that is onto, or it maps onto its codomain, then we say that function is a surjection, or we say that it's a surjective function. Again, that term is not really going to show up in your book as far as I can remember, but it is a term that's used in a lot of literature, surrounding this subject. So I'm going to start with a theorem. This is a really important theorem, and we're going to expand on this theorem in another theorem that comes later. So if you have a linear transformation, and I'm missing the T here. If T maps V into W and it's a linear transformation, then T is 1 to 1 if and only if the kernel of T is just 0. Now remember, we showed in the last section that the kernel of T is a subspace of V. Remember, it's the set of all vectors that are mapped to the 0 vector, or have 0 as their image under this linear transformation. We know that the 0 vector is always mapped to the 0 vector for any linear transformation. We proved that. So the 0 has to belong to the kernel no matter what. What we're saying here is that if T is 1 to 1, then 0 is the only vector in the kernel of T. So to prove this, it says if and only if, so we have two directions to prove. Let's begin by assuming T is 1 to 1, and try to use that assumption to show that the kernel of T is just the set containing the zero vector in W, or sorry, in V. So we already know, like we said, that the image of 0 is 0. The zero vector in V maps to the zero vector in W. This is something we've proven. So we know that the zero vector is in the kernel of T. But let's suppose that we just choose V to be any arbitrary vector in the kernel of T. Because I'm selecting V arbitrarily, if I can show that the assumption that V belongs to the kernel implies that V equals 0, then that would mean that 0 is literally the only thing in that set, in that kernel. So let's see what we can do with this. The assumption that V is in the kernel of T means that T of V equals 0. That's the definition of the kernel. Any vector in the kernel maps to 0. But we also know that T of 0 is equal to 0, like we said up here. So what we have is T of V equals T of 0. By the definition of what it means for a function to be 1-to-1, that implies that these inputs are equal to each other. In other words, V is equal to 0. That proves what we wanted to prove. The kernel is the set containing the zero vector in V. Okay, so that's one direction. Now let's prove the other direction. Let's suppose that the kernel of T equals 0. Can we show with this assumption that T is 1-to-1? In order to do that, remember, in order to establish that something's 1-to-1, we need to prove this property. We need to show that if you have any pair of vectors that have the same image under this linear transformation, then they must have been the same vector to begin with. Okay, I'm seeing all these little typos in here. There shouldn't be a comma there. All right. So what we're going to do is pick two vectors in V such that their images are equal to each other. And the goal now is to use this assumption that the kernel of T is 0 to prove that this implies that V1 is equal to V2. That would establish that we have a 1-to-1 transformation. So if this is the case, I can subtract T of V2 from both sides, and I get T of V1 minus T of V2 equals the 0 vector. However, because T is a linear transformation, I know that T of V1 minus T of V2 is equal to T of V1 minus V2. Right? We proved this property of linear transformations in 8.1. Now, I'm going to use my original assumption. Remember, the kernel of T is the set containing the 0 vector. So any vector that maps to 0 under this linear transformation must be equal to 0. That's what that assumption means. Therefore, V1 minus V2 is equal to 0, and adding the V2 to both sides shows that V1 is equal to V2. That proves that T is 1-to-1. Okay, so this gives a criteria for checking whether or not a linear transformation is 1-to-1 without having to use the definition of 1-to-1 directly. It gives us an alternative, which is actually really useful. All right, let's work on this idea for a second. So I want to show that the linear transformation that maps M22 into R4. So M22, remember the set of the vector space of 2x2 matrices, and R4, ordered 4 tuples. Defined this way is both 1-to-1 and onto. So this is the linear transformation that takes these 2x2 matrix A, B, C, D and maps it to the vector A, B, C, D. We need to show both of these things, that it's 1-to-1 and onto. Now I can prove the 1-to-1 property using the definition of 1-to-1, and that's actually easy enough to do in this case, but let's practice using this theorem. I showed up here that a linear transformation is 1-to-1 if and only if the kernel of that linear transformation is 0. So again, if I have this, let's say suppose T of A, B, C, D is equal to the 0 vector. 1, 2, 3, 4. So this is the 0 vector in R4, 4 zeros, right? What I'm doing here is I'm saying that let's suppose that this vector in M22, this 2x2 matrix, is in the kernel of T, because if it's in the kernel of T, then it's going to map to 0. Okay, but from the definition of the of this transformation, and by the way, back this up for a second, we didn't prove that T is a linear transformation. We're just taking it for granted that it is. It's very easy to prove that this one's a linear transformation, But the goal here is to say, once we know that it's a linear transformation, we want to prove these two properties. So I'm skipping that first part. Anyways, from the definition of a linear transformation, these four coordinates in R4 are supposed to correspond to these four entries in that order. A, B, C, D should equal 0, 0, 0, 0. So I could say then A equals B equals C equals D equals 0, right? So this vector, the kernel of T is equal to the set containing only the 0 matrix, which is the 0 vector in that space, right? Because this is the only vector that can do this. So by that theorem, therefore, T is 1, 2, 1. Okay, and again, like I said, it's not difficult if you get a little practice with this, proving that this is a one-to-one transformation just using the definition of one-to-one. But it's actually faster to do this. Now, notice that doesn't establish that this is onto. We're going to show in a theorem that follows that this actually does suffice to show that T is also onto, simply because the dimension of these two vector spaces is the same, but we haven't proven that yet. So I have to go with I have to use the definition of onto. How do you show that a linear transformation is onto? Well, remember, by definition, onto means that every single vector in R4 is the image of a vector in M22 under this transformation. So what I do is I let A, B, C, D be just any arbitrary vector in R4. And now the goal is to find a matrix in M22 that maps to this vector. Well, we know what that would be. Then T of A, B, C, D equals A, B, C, D. So T is onto. It seems like we didn't really do anything there. I basically just restated what this linear transformation does, right? What it's defined to be. But if you think about what we just showed, we showed that any vector in R4 shows up as the image of another vector that lives in M22, so that nothing in R4 goes unused by this linear transformation. That shows that this linear transformation is both one-to-one and onto. Now, in section 8.3, we're going to cover part of 8.3 in another set of videos. Should actually just be one video for that one. We're going to come up with a term for functions that are both one-to-one and onto. A linear transformation that satisfies both of these properties is called an isomorphism, but we're not going to really worry about that term until we get to 8.3. So one example under our belt. Let's look at a couple more. Here's another linear transformation. And again, we're not proving that this is a linear transformation, even though we easily could, just because the goal is to talk about these two terms, onto and one-to-one. I'm going to let T be the linear transformation from P2 into R2. So the set of all polynomials of degree 2 or less, mapping into the set of all ordered pairs in R2. And this is how we're going to define this linear transformation. T of ax squared plus bx plus c equals the ordered pair AC. Okay. Notice the b here doesn't end up being used anywhere in this image. What we want to do is show that this is onto, but not one-to-one. So again, we just showed in the previous example how to prove that something is onto. You pick an arbitrary vector in the codomain. I say let x, actually I don't want to use x, let's call it AC. Let's let AC be some vector in R2, okay? The goal is to say I can find a vector in P2 that has this as its image. Now notice, again, from this definition, the b, the linear coefficient on this polynomial, doesn't get used anywhere. So I can let b be anything that I want it to be. I can let it be 0 if I want. So I can do this. Then ax squared plus c is in P2, and t of ax squared plus c equals ac. So I've located a vector in P2 that has ac as its image. Thus, t is onto. Okay. Now I could have gone with other vectors as well, right? I could have used ax squared plus x plus c, because then the linear coefficient, which I'm calling b here, would be a 1, but it still would map to the vector ac. And that actually kind of reveals why this is not 1-to-1, because by changing the coefficient on b, I can find more than one vector in P2 that map to the same vector in R2. And that's how we show that something's not 1-to-1. I find two distinct vectors in my domain that map to the same vector in my codomain. So let's show an example of that. However, t of, let's say, x squared plus 1 is equal to, this would map to the vector 1, 1, right? Because, again, it's my leading coefficient in my first component and my constant term in my second component, 1 and 1. But this is also the image of this point, x squared plus x plus 1. Right? So, again, leading coefficient and constant term are both 1. These have the same image. The inputs were not the same vector. So this can't be 1-to-1 because of that. Since x squared plus 1 is not equal to x squared plus x plus 1, t is not 1-to-1. Okay, and this kind of goes back to something that we talked about early in the course about how to prove that something is not true. So if I'm trying to prove that this function, this linear transformation, is not 1-to-1, what you can do is find a counterexample. Find specific vectors that show, once you use this kind of an argument, that this function is not 1-to-1. I don't need to prove something general like I did here. Notice I didn't pick a specific vector here. AC is an arbitrary vector, but I'm using specific vectors for a counterexample. Let's do another example, but doing sort of the opposite of the last one. I have a linear transformation going from Pn to Pn plus 1, and we talked about this one in section 8.1. It maps polynomials in Pn to the polynomial x times p of x. And what we want to do is show that it's a 1-to-1 linear transformation, but that it's not onto. So again, I can use the definition of 1-to-1 if I want, or I can show that the kernel of this linear transformation is 0 to establish that this is a 1-to-1 transformation. So in order to do that, let's let p of x equal, or sorry, not equal. Let's let p of x be a polynomial in p of n such that t of p of x is equal to 0. Remember, the 0 vector in Pn plus 1 is the constant function 0. Well, what am I actually doing here? I'm saying p of x belongs to the kernel of this linear transformation because it maps to 0. The goal here, using that previous theorem, is to show that if this is true, then this polynomial must have been the 0 vector in the first place. Okay, so to show that, remember what this does is it takes our polynomial that we're using as an input and multiplies it by x, right? Now here's where it's really important to understand the difference between 0 being a solution to an equation and 0 being the constant function. I am not saying that this is a solution to this polynomial. I'm not looking for roots of this thing. This is the 0 function, which means this needs to be true for all values of x. Now if it's true for all values of x, I'm not thinking of just plugging 0 into this. That doesn't work, okay? So I see a product here, and according to my zero product property, one of these two things must be identically equal to 0. Well, x is not identically equal to 0, because again, I'm supposed to think of this as a function. The function f of x equals x is different from the function f of x equals 0. By the zero product property, this is from algebra, x can't equal 0, so p of x must equal 0. Namely, the zero function, right? So that's what I wanted to prove, because this says if you pick an arbitrary vector in the kernel of t, it can be shown that that vector has to be the zero function, or the zero vector in Pn. That establishes this one-to-one property. Therefore, t is 1, 2, 1. Okay? Now, how do we show that this vector, this linear transformation is not onto? Well, if you pay attention to what this function does, it multiplies vectors by x. What that implies is that the constant term of any image of under this linear transformation is always going to be 0. Why is that? Well, if you look at the input, p of x, whatever its constant term is going to be multiplied by this x. Now it's not a constant term anymore. It's an x term. And you're not going to magically pick up a new constant term in that process. So this will never have a constant term of anything other than 0. However, p of n plus 1, the vector space, contains all constant functions in addition to all polynomials of degree n plus 1 or less. So there's polynomials in here that never show up as images under this linear transformation. How do we state that? Well, again, use a counterexample. Actually, I'm not going to quite state it that way. There doesn't exist a polynomial in Pn such that p of x is equal to 1, since, I'm sorry, I don't know why I put a p there. There should be a t. T of p of x, since t of p of x, which equals x times p of x, must have a constant term of 0. Therefore, t is not onto. Okay? So that's 3 examples. One where the linear transformation is both one-to-one and onto. One where the linear transformation is onto but not one-to-one, and then vice versa for this example here. Okay, so in the next video, we'll start looking at some important theorems to expand on this idea and kind of move along with the idea of compositions and inverse linear transformations.